Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Today our group will present about the research project titled Designing and Building a Rankine Steam Cycle System. So for our group member, the first one is our leader, Awang Muhammad Hanif Akmal bin Awang Syarbini. The next one is Abang Muhammad Hakimi bin Abdullah. And the last one is me, Farhan Azir Aiman bin Muhammad Rafi.
For the abstract, we designed two steam turbines using the Rankine cycle, one producing a 10 megawatt and the other a scale-up version delivering 20 megawatt. Both systems were modeled in Aspen Hysys, a process simulation tool used for energy and fluid flow analysis. The key components included the boiler, turbine, condenser, and pump. We perform a mass and energy balance calculation to compare system efficiency and assess the effects of increasing power output. For the introduction, the growing demand for reliable energy, especially in industrial zones like Samajaya Free Industrial Zone in Kuching, has increased interest in thermal power cycle. The Rankine cycle, known for its efficiency and adaptability, is widely used to convert heat into electricity through a pump, boiler, turbine, and condenser loop. Mus Elf Sedian Berhad, a steam turbine consulting firm based in Kuching, was contracted to design a Rankine cycle system producing 10 megawatt of net power. A, a second project involved upgrading the system to 20 megawatt, requiring a redesign and performance evaluation. This study used Aspen HYS to model both systems, focusing on mass and energy balance, thermal efficiency, and design improvement to meet higher power demand reliability. This is our objective and the aims for this project. We designed a Rankine cycle system capable of producing 10 megawatt and 20 megawatt net power based on thermodynamic principle. Two, we simulate the Rankine cycle using the Aspen HYSS with accurate thermodynamic data. For number three, analyze and compare both systems in terms of mass flow rate, enthalpy change, energy conversion efficiency, and equipment performance.
For this Rankine cycle, we'll be using Aspen Hysys to simulate the entire process. There are four main components for this cycle, which are the pump, the boiler, the turbine, and the condenser. And then the properties of the fluid, stream, and components are set to a certain value until the net power reaches 20 megawatts and until it reduces to 10 megawatts. So this is the Rankine cycle simulated within Aspen Hysys. For the 20 megawatt Rankine cycle, the flow-to pump has a pressure of 73.70 kilopascal with a temperature of 33 degrees Celsius. Afterwards, the flow to turbine has a pressure of 6,700 kilopascals with a temperature of 500 degrees Celsius. And flow to boiler has a pressure of 1,000 kilopascal and the temperature of 33.09 degrees Celsius. And then the flow to the condenser has a pressure of 83.70 kilopascal and the temperature of 101.5 degrees Celsius. For the 10 megawatt Rankine cycle, the flow to pump stream has a pressure of 1,177 kilopascal with a temperature of 33 degrees Celsius, and in the stream for the flow to boiler has a pressure of 1,500 kilopascals with a temperature of 33.03 degrees Celsius. Then the flow to turbine has a pressure of 6,700 kilopascals with a temperature of 500 degrees Celsius. And then the flow to condenser has a pressure of 1,187 kilopascal with a temperature of 297.7 degrees Celsius. The Rankine cycle power output is affected by four different factors: pressure difference across the turbine, the condensate pressure, the steam temperature and superheated condition, and then the turbine and pump efficiency.
Assalamualaikum. My name is Farhan Azir Aiman bin Muhammad Rafi, metric number 104127. I will talk about the discussion. So, for 20 megawatt system, the turbine pressure drop is 6,616.3 kilopascal. So, the condenser pressure is 83.7 kilopascal. The steam temperature is 500 degrees Celsius, so we can say it as superheated. And from this, we can see the more expansion is equal to the more turbine work, and it's become the higher power. And for the 10 megawatt system, the turbine pressure is lower. It is 5,517 kilopascal. The condenser pressure is 1,187 kilopascal. From this, we can say the less expansion equal to less power output. Mass flow rate above equal for 10 and 20 megawatt system. The output change is due to the pressure setting. The superheated steam at 500 degrees Celsius are used to improve quality, reduce moisture in turbine, and protect equipment. By using the superheated steam inside the equipment, there is no moisture that go inside the system. So that makes the equipment will be more last longer. So next one is for the efficiency. Both turbine and pump are at 75% for both system. This is for make it a fair. As we can see, the more pressure difference are equal to more power, and lower condenser pressure is equal to better cycle efficiency. So here is the last one from us. It was a conclusion. So in the conclusion, we can say the simulation show Rankine cycle can be scaled from 10 megawatt to 20 megawatt by adjusting the pressure. The main difference was the higher turbine pressure drop and lower condenser pressure in 20 megawatt system. The efficiency and the steam temperature stayed the same, so output difference was due to system pressure design. The lower condenser pressure improved turbine expansion range and cycle efficiency. The Rankine cycle is flexible and widely used in industrial power generations. That's all from us. Thank you.